Now, something that I can't teach at Georgia Tech, but I've taught elsewhere, is one could teach quantum chaos, and then this course is preparatory for that one. And quantum chaos you cannot do in any other way but with the fancy footwork. You really have to know quantum mechanics and this much nonlinear dynamics that we know now to be able to predict something like spectrum of helium. Now, that's a very good example of Indiana Jones again. Helium is immensely important in the history of physics because, by 1916, Bohr had a credible model of hydrogen. It was a little bit weird, but it was working well, and there were also all kinds of other crazy models, like, supersymmetric models or something. Some, models that could all explain sequence over 1 over n squared, the Bolmer series, which is what spectroscopists observe. But what Bohr was able to do is he was able to use his theory to also predict once ionized helium. So this is a atom like hydrogen, but it has 2 charges instead of 1 in the middle. And he predicted this with 6 accurate digits of accuracy, and that was real prediction, and they measured it, and that's why Bohr's model was good. Then he was very perplexed, being a young man. He said, well, I did hydrogen, but nobody will believe me because there are all these other atoms one has to do. He confided to his postdoctoral advisor, Ernest Rutherford. And Rutherford said, don't worry, if you show it for 1 and 2, they'll believe the rest, this being physics. So you just had to do hydrogen. So they spent next 18, that's maybe exaggerating, but they certainly spent at least 6 or 7 years working on hydrogen. It was Kramers and Bohr who worked on hydrogen. And at some point, Heisenberg figured out matrix formulation of quantum mechanics. And the reason why that was credible is that he predicted a credible ground state of ortho and para helium. And this language was very different from Bohr, Sommerfeld, etc., planetary model of atom. So they were all happy to just junk the planetary models and throw some in quantum mechanics. And this thing was amazing. It had an early run, so people like you would all have Nobel Prizes if you were graduate students in the 1920s. It would just give you a problem and you would invent condensed matter physics. So, give you a problem, you invent a subject. So that was a great run, and it worked at least until 70s or 80s, all the way into the particle physics and kind of particle physics that we can reach experimentally today, including Higgs and Standard Model. So this stuff worked. So, and helium was done Indiana Jones way. You put it on a computer. This was already done in the 60s. My advisor did it, my graduate advisor. Variational function, with 1,000 functions, 1,000 parameters for the ground state wave function. You stick it into the Ritz or Ritz-Rayleigh method, and you get a ground state, and you get it measured experimentally. And these are all amazing numbers because, spectra are measured to astounding accuracy of 10 significant digits, and etc. So this stuff works, and then it became quantum chemistry, which is a huge subject, and band structures, etc. And it's all Indiana Jones stuff. I mean, you know what you want to do. You have material you want to describe. You crunch some computer. There's some intelligence goes into inventing, the right codes and thinking. So there's actually a Nobel Prize for that a few years ago. And you get the answers. So nuclear look reasonable. Lots of stuff comes out, and it's a bunch of numbers that you can measure. But there is this nagging thing, you don't have much intuition about it. a person who is good with fancy footwork and so would like to understand how this works. In particular, you would like to understand, is there some connection between equations I put in, dynamical equations that describe interaction between electron and proton, or two electrons and nucleus, and the result. That was done by a person who did both things, could shoot and could think at the same time. His name was Martin Gutzwiller. Martin Gutzwiller combined his passion for dynamics of the moon, celestial mechanics, his passion for classical books in mechanics, and his day job, which was silicon and germanium at IBM, understanding the transfer properties of these things. And he invented chaos, meaning he invented trace formulas and zeta formulas of kind I described in this course. But it was done in the quantum context, and it was done in the context of semi-classical or Wkb approximation. So he established that you could start with your equations of motions of electrodynamics, and from the motions of electrons, two electrons moving, he didn't do that problem, but it was done in the 80s by some much younger people. Of the motion of two electrons, a nucleus classical motion, three-body problem in this particular case, one could eventually compute the spectrum of helium rather well. Now, this is not as good as shooting with a gun, because if you put it on a computer, you get more accurate spectrum of helium. So if you just program it and run it, but it gives you lots of intuition. You start understanding that certain motions of these things correspond to certain spectral behaviors, and if you put magnetic electric fields, you can get all kinds of amazing physics from having this connection of understanding chaotic motion of the system and what you observe at a long time, which is typically lifetimes, spectral lines, widths, responses to external fields. So there's lots of good atomic physics that comes into it. So this is a wonderful thing. Because this happened, I was not interested in the problems that Gutzwiller was interested in, but just the fact that there was a way to understand complicated motion and connect it to prediction of the spectra was a strong motivation for me to learn that subject. Now, my motivation was somewhat different. It can be said in a very simple way if you have had a quantum field course or a statistical mechanics course. But typically there's some kind of partition function that describes either statistical or quantum system. And since time of Dirac and Feynman, this can be done incredibly compactly. It can be written in this way. I over h bar means you're doing quantum mechanics. In this course, hidden to the naked eye, we had 1 over sigma, where sigma was noise, but and noise was very small. It's kind of justifies stuff we've done so far. And then there is a law of motion, which is hidden in what's called quantum action. There's some operators, so operators are derivatives, if you wish. There's some kind of source term. And now, this summarizes in some way all of the quantum mechanics and quantum field theory. The big deal is to figure out the details of the laws. So what kind of particles you have. So you might have photons, You might have gluons, meaning photons which carry color. You might have electrons or anti-electrons or particles of higher spin, bosonic particles, various couplings. And they obey certain symmetries, and all of that is summarized just by one function, which is the action. A modern generalization of Hamilton's insight that one could describe Newtonian mechanics just by writing Hamiltonian, that everything followed from one scalar function. The way that this theory is used, for me this is really statistical mechanics, quantum mechanics, stochastic mechanics. So a great deal of theoretical physics is somehow encapsulated in this way of thinking. And this way of thinking says that there is another representation for this whole thing, which is called a path integral representation. And the way that this is used in practice is one literally sums up all the paths. So that's called lattice gauge theory. Shooting the gun, in this case, requires fat beta, requires a real artillery piece. When this was invented in the 80s, the original idea came from Ken Wilson, and then other people implemented it. They used to actually build specific computers. They would build computers just to do lattice gauge theory calculations. Now that turned out not to be a good strategy because the development of computation for other reasons, nothing to do with physics, was so fast that by the time you build this machine, processors which are commercially available were cheaper. So it went to supercomputers. And it gives you something. And it literally what it does is sums up all these paths. So this is path integral. In some sense, it's unsatisfactory unless you just like to kill problems and move on. But if you're interested in understanding, this is a difficult way to gain it, I feel. But I respect the work. I've had colleagues who have gone into this and then told me it's like working in a factory. You come to work, you sit in front of a computer, and you run for 8 hours, and then you go home. So they would do this for a while, then they will go back and do other kinds of physics. It's hard. Now, what Gutzwiller realized in one case, so this is everything, but he did it for atomic physics or ordinary non-relativistic quantum mechanics, kind of quantum mechanics that you are taught in the school, but you never taught the chaotic version. A decent course, I don't know where we teach decent courses, but a decent course should teach you Wkb method. This is Brejon, but Wenzel, Kramers, Brejon. So this was done almost immediately, like immediately after Heisenberg, and Schrödinger wrote 2 versions of quantum mechanics. These people said, that's wave mechanics, we know how to work with wave mechanics. The way is to find caustics or extremal trajectories. And that's the Wkb method. And what Wkb method does is it says such thing is dominated by classical behavior. And you might ask yourself, how could quantum mechanics be dominated by classical behavior? And they might have taught you some that it should be so for high energies, high quantum states. But it turns out Wkb works very well for the harmonic oscillator and hydrogen written in proper coordinates. It'll actually give you the exact answer because, it's a Gaussian approximation to potential that has more structure than just being Gaussian. So it assumes that things are locally Gaussian. And the result, though, is that the path integral becomes a sum of, you'll be very heartened to hear this, periodic orbits. And they're classical. They're this variety we do in this course, and they're the same as, it's a sun. And then this whole thing, it turns out, the way I think about it, and maybe other people too, is that there is a landscape. There's lots of mountains. And the vertical axis is this action here. So it's a function that depends on variables. And the horizontal axis are whatever basis you're using to describe your wave functions, these phis, these functions. And in quantum mechanics, the basis is really just our space on which we define the wave function, but in quantum field theory, it's just like in fluid dynamics, it's just defined every place in a space. It's an infinite dimensional system. So there are lots of coordinates here. I don't know what to call them, x1, x2. x2 kind of nest infinity. And this, what Wkb says, this integral gets a significant contribution when there is no variation in linear term. So when this is extremum of the action. So these are the important. And when you go through the work, you realize that these are actually classical solutions of equations of motion that are extrema. And this is a very general thing for any quantum mechanical problem. So this now becomes I over H. So quantum mechanics is sitting in here. But this is actually computed on a classical solution. So if you can solve classical partial differential equation and find solutions of it, then you get a good approximation to this partition function as a sum of classical solutions. And if you want to be more devious, this is actually just the beginning of a series in H bar, because the first term captures behavior, quadratic behavior of the Cetelon. Higher terms capture more nonlinear behaviors than just that in the problem. So there is a set of corrections here, H to the end, for infinity. These things are computed by various methods, but the one that you might have heard of, they're computed by Feynman diagrams. So there is a set of corrections.